This video is brought to you by Hygromo Chalk. Use code TPSA 10% off to get a discount.
Okay, welcome back. In this video, I'd like to talk about vectors, more about index notation, specifically contravariant and covectors, and then as well as about tensors and more about the metric as well. Okay, so first we're going to discuss vectors in general relativity. So vectors in general relativity are a little different in that the quantities that general relativity is concerned with are abstract vectors, which are not so like vectors v, which are not given a certain preferred coordinate system. The vectors should be valid in all coordinate systems. That's why I don't have any axis drawn here. I literally just have a vector. Now, of course, for us human, for our brain, this is very hard to understand and deal with. So we naturally want to expand over some basis. So my basis are these vectors v with some components v. Now, what I'm doing here is I'm using some Einstein convention. I have two indices. Don't worry about whether they're up or lower for right now. I'll explain that later. I have two indices. So what this means is I have some v1 times some vector v1 plus and that will sum together to give me some vector, right? So this is what we're going to be dealing with. And now, we're going to be dealing with the components mainly, a little bit with the basis vectors, but it's the components that we'll mostly be dealing with because they're easiest for us to pick out some coordinates, then talk about the coordinates. But in the background, what really is going on is these vectors that are independent of coordinate system, and that's very important for GR. Okay, so let's talk about some different type of vectors. So in the last lecture, I said we can group space and time together, and that made us a 4-vector. But what we're really dealing with were points. They weren't actually vectors in the sense of having a magnitude and a direction. They were just kind of grouped in a vector way. They were still points. If we want a vector quantity, well, we need to think about where we're going to get one from. The first place we come across vectors in physics is some sort of velocity vector, right? We have a particle's trajectory, and we can use a derivative at a certain point to give us a vector. So let's start there. I'm going to define a vector with an upper index to be. So you can see for this, we need some curve through time. So I'm going to say this is a curve where the points in the curve are given like this. So this is lambda is some real parameter. So you can say that lambda is a map from the real line to whatever our space is. We call it a manifold M, right? Okay, so lambda maps like this. Sorry, X is lambda. Maps like this, right? So given a point, you can start lambda at 0, and it can go to 1, and it'll map some line through our space. Then the velocity vector is going to be defined as the derivative of this mapping with respect to the parameter. Now this seems very arbitrary. I could change this parameterization by a constant or anything really, and it would still kind of could be the same form. But we'll find that in general relativity, there's a certain parameterization called an affine parameterization that will be most convenient to do it, and that's what we'll end up using. So this defines a vector, and this is when I'm going to define a vector with an upper index. So now, if we are being humans and we're dealing with these components of vectors, we're going to have to figure out how these transform. So I here was using a set. I've picked a set of coordinates x, right? This could be like my x, y, z, and t. But I could also pick some other coordinate system, call it y, right? Y, u. This could be like my spherical coordinates. Now, if we do this, then it'll implicitly, what we'll have is our old x coordinates will be a function of y, and the old y coordinates will be a function of x. Think of like, you know, or cos theta, right? X is a function of or and theta and vice versa, right? So there'll always be some linkage between them. So, well, what if I wanted to describe this vector in this new coordinate system y? How does this change? Well, that's not too bad. I just do the chain rule, right? But I need to be a little bit careful, right? Because I'm dealing with multiple quantities. So how does the chain rule look like? So you may remember that, like, if I have a function, we'll keep the same. So, okay, I have a function x, which is a function of several variables, y0, y1, y2, right? We'll go to, yeah, now you can be up to like, maybe d dimensions, right? D-dimensional space, and whatever I want. So this is a function of this. What does the differential dx look like? Well, like this. I'm studying multivariable calculus. This is going to be the partial derivatives. So it can be partial x mu, partial y, 0 d y0 plus all the partial derivatives, right? So it's d minus 1, dy, d minus 1. Okay? That's what that's going to look like. Now, this is really messy, but there's a beautiful thing. Index notation, I can see I have 0 and a 0, and I'm summing. So let me just write this in index notation. dx mu, dy nu, the Greek letter nu, and then this is just dy nu. Okay? So index notation, and then we can see, well, what does this look like? I can divide by my dx nu, and I have dx mu over dy nu equals, so sorry, this is kind of like, I'll divide both sides by lambda, right? So dx mu d lambda, because that's an important thing. Right? And you can see that this is kind of like the chain rule. It's kind of like I cancel these two things and I get back my dx over d lambda. So index notation, in a way, kind of restores the chain rule from complicated partial derivatives, which is really, really nice. So let's do this. Let's plug this in now. So we have dx d lambda, and now we know it's equal to this. So on our transformation chain, partial x mu, partial y nu, then we have dy nu d lambda. All right? Well, what does this look like? Well, this is, if we were to define a vector in the new coordinate system, let's say call it v prime nu, brackets, you know what's going on there. This would be exactly it. This would be dy nu, because that's the same as this definition here, just in the new coordinate system. With respect to lambda, and it's the same form. Okay, so what this tells us is that our new vector is related to the old vector if I was to divide, basically invert this. So the y is going to go on top and the x is going to go on the bottom. dy nu dx mu, and then I get my old vector, because I've basically put this on the other side. This is a very important equation. This tells us how my components change if I make some general coordinate transformation. Now this will be very useful. Now I can define this to be how, so I will say that any vector with an upper index is defined to transform in this way. Okay, you may be thinking that might be all vectors, but I'm going to show in a second that you can get different type of vectors. Okay, so let's leave that there for a second and go over here. So that's one way. As we go through physics, we go along, we might come across different concepts and in that way different vectors. So I might like be dealing with some sort of like heat equation where each point in space is given a certain value of temperature. Then you might, to develop some theory of thermodynamics, you've got to take some derivative of this temperature field. So let's say I have a function x. So this just maps back from my manifold to the real line. So it's just a number everywhere in space. Then the quantity df of x dx mu. So that's like, it's going to be like a vector that each of the components are derivative of f with respect to each index. So I'm going to define this equal to a vector with a lower index. Now, why is it a lower index? Well, because when I make a transformation, so I'm going to make a transformation. So I started with x mu, and I'm going to change to y mu as I did before. Then we're going to do the chain rule again. In this time, the chain rule is with partial derivatives. So that chain rule looks as followed. dx mu. Right? If you remember from vector calculus, this will just be dy 0. But it's instead with the y's on top and the x on the bottom. Right? It will look like this, and the same here, right? Y d minus 1, x mu, then partial derivative, y d minus 1. Okay, we can then, again, use index notation, write this as dy nu dx mu d dy nu. So then this looks very much like cancellation we get from just applying the chain rule. The index notation nicely gives it back. So this quantity, how does it transform? Well, we just do the chain rule over here. We're going to get dy nu dx mu df dy nu. Okay? So now f was a function of x, and x is a function of y. So I can just write my y there. Okay? Very, very nice. Well, now we can check, well, if we were to write this w vector in terms of y, this is exactly how we would define it. So this now is our w prime, where now is an index mu. Okay? We can do the same thing, right? These two equations are equal. So I can move this partial thing to the other side. So I get that this prime is equal to, now with an x on top, dx mu dy nu, and then this is going to give me back my original vector. Okay? And now we compare those two equations. We now see that they're different. Over here, the y is on the top, and the index is canceling, or kind of contracting in the bottom. But here, y is on the bottom, and it's going like this. So we can kind of consider this thing has two indices. So it's going to be like a matrix, and this matrix transforms the vectors from one frame to another. Okay, then with these, okay, I need to give them names. This is called a contravariant vector, and then this is called a covector or a dual vector. And so there's one last interesting thing I want to look at. All right. Probably should have left them there, but that's fine. I'll leave one of them there, and we know that the other one transforms like the inverse. Okay? Okay, now I want to consider, well, what if I do this? So this is index notation. This is kind of like I'm dotting the two vectors together, right? I'm considering the two components and I'm summing over them. So this will be W0, V0 plus W1, V1, and so on. So kind of like a dot product. But I want to consider this. I want to say, okay, what happens to this if I change from coordinates x mu to some coordinates y mu? What happens to this? Well, this is going to so this is going to change quantity. It'll become W prime mu and V prime mu. We know what these are. We already calculated them. Okay? The W prime mu is the same as this, but remember I said it's inverse. So it's dx mu. Oh, we already used mu, so this is going to be, I'm going to call this alpha. dy mu stays the same. And then we got W alpha. Okay? That's the first bit. It's just this. Then this second one will change like this. So start with a mu up here. So we'll just switch the indices. So this is going to become dy mu dx, I'm going to call it beta, and then we get v beta. All right, a little messy, but what if I look at these things? These are multiplying, and I can see that I have a dy mu and a dy mu. But I was just discussing how in index notation, the chain rule kind of gets restored to us. Because these are the same index, dx alpha, dy mu, dy mu, dx beta is equal to simply just dx alpha over dx beta, right? That's because this is literally, this expanded in terms of y is by definition this, okay? Now, what is dx alpha dx beta? Well, that is just like if I have x0, x1, and so on, and I take derivatives with respect to dx1, dx2, well, we're only going to get these, by definition, are points in space and have to be independent. So the only time we're going to get something non-zero is if we're taking a derivative of the zeros with respect to the zeroth index. Then we get like something like dx0 over dx0, and that's just 1. That's just like the derivative of x with respect to x is 1. So this is only 1 if alpha and beta are the same. We saw that quantity before. It's the Kronecker delta, but I'm just going to put an alpha and a beta up here. Now, what the Kronecker delta does, it says, okay, alpha must equal beta, or alpha beta. Alpha must equal beta, otherwise this is 0. So I have an alpha and a beta, but I've said, oh, they must be equal to each other, otherwise they're 0. So this is W alpha V alpha. And we can look, that's exactly what I started with. So if I get any covector, anything that anything that transforms like a contravariant vector, anything that transforms like a covector, under any transformation of my coordinates, they remain unchanged. So example for this would be like our proper time, like we saw in the last lecture. It's invariant under coordinate transformations because it's a contraction of an upper index with a lower index. So that's why we use this. Now, this is great because of the principle of general covariance, which is, so there's two postulates of GR. There's our principle of equivalence, which I talked about, and then the second postulate of special relativity, which says the laws of physics must be the same in all inertial frames. General relativity extends that to non-inertial frames. So non-inertial frames may be, that means I should be able to make any sort of transformation, not just like a Lorentz boost, which is linear, and I should get the same results. So if we can build our theory out of quantities like this, which are invariant, then we'll be good to go and we will be satisfying that postulate. Okay, so with this setup, we are now ready to talk about the main building blocks of general relativity, and that is tensors. Okay, So we have seen so far that objects with upper indices transform like this, all right? And you may recall the objects with lower indices you transform the opposite way with the x on the top and the y on the bottom. I'm going to make that new, and then this will be new. Okay. So tensors are where we extend these objects to have multiple indices. Okay. So what I mean is, if I have any tensor and it has a k of these indices, could be all upper, and then it could have s of these lower indices under transformation, where I send x mu to some other coordinate system y mu. This will become a long list of stuff. So for the upper indices, we can see that it's going to get dy over dx, and then I'm going to call this sigma 1, and then so it'll get k of those. Okay, so then mu to k all over dx sigma k. And then for each of the lower indices, it's going to get some of these. Always multiplying on the outside. So now it's going to be dx and rho 1 dy new 1 all the way dx rho s all over dy rho s. Okay, and then that's multiplying our new tensor t prime, which will have indices 1 sigma k and rho 1 up to rho s. Okay, very messy. But that is our definition of tensors. Okay, when I was talking about the start, I mentioned that we always have some vectors, and these are just the components. In the exact same way, these t are just the components of the tensor. For each index, they have attached to them some basis. Now, because they're multiple component objects, the bases are a little more weird. If there's like two indices, they might be like, for example, this would be a matrix with one index. This would be like, and then you would expand over all possible places of the one, and that would be your basis. So the basis components for these will look a little different. Okay, so quite unsatisfactorily, a tensor is defined as something that transforms this way. This is important, as when things transform this way, when we combine these objects such that we have all upper and lower indices contracting, as I said earlier, when we have an upper and a lower index, that forms an object that is invariant. So just this way, these tensors, when we contract them with their bases, will be invariant objects that we can use in any coordinate system, and they'll always satisfy. So if we write down laws of physics in terms of tensors, we will automatically satisfy the principle of general covariance. That's what we want to do. So that's why we use tensors, and this is how they look. Very, very messy. But let's make it simple. Let's talk about a rank 2 tensor. So these are rank 1 tensors, these vectors. Let's talk about a rank 2 tensor. Probably the most important tensor, the metric, as I've been talking about earlier, or in some last lecture, I believe. Okay, let's leave those there for now. Okay. So metric, I'm now going to G, and I'm going to give it 2 indices for now. Okay, so if I have any vector, and we saw in the last lecture that if we have a point, we have like a 4 vector point with time and our space components, we can calculate an invariant length, so it shows us proper time. We can do the same with any vector. We can get an invariant length, you can so say. So this is how we would compute it. Okay, so notice we are summing, so we slam our matrix in the middle, and we have our two vectors, and we sum over all the indices, right? That's exactly the same form we had earlier, right? We had some vector, a matrix, a vector. If you write that out in index notation, it'll look exactly like this, just obviously with some summations in front of it. So this is the same thing, that's how we write it. You can also remember we wrote it in Kronecker delta, we had like alpha, beta, dx alpha, dx beta. That's exactly what we were writing, exactly this form. These were our vectors in that case. So this is how we calculate length. Let's do an example. So let's say we're in flat space. So remember our metric was -1, 1, 1, 1. Well then, so I'm going to call that metric the Minkowski metric, and I'm going to denote it with an eta. So in that case, we had like a V0, V2, V3. Our matrix will look like this. We get a minus. And right, we'll get something like this. And this is very familiar. We'll get V0 minus V0 squared plus V1 squared plus V2 squared and so on, okay? Okay, so that's pretty familiar quantity. Now, what I want to check is that when I transform, we must have that the transformed quantity is the same in both frames. So I transform each of these things when I transform. So what I mean by transform is I was originally working with some coordinates x mu, and I changed to y mu. That's always what I mean by transform. So each of these is going to become a prime, right? In the new frame, including my metric. It's going to come g prime and b prime again. Okay? We know how these transform. That's given by this law down here. Okay? Now, I want to use the fact that this must be equal to this because I want my length to be invariant. And I'm going to see, well, what does that do to g prime? What does that make it look like? Okay, well, let's use this law. So this first one, dy mu, dx nu, let's call it alpha. Dx alpha, v alpha, so that's my original v. We'll get my g prime mu nu. Then we'll get the same again, dy, but for the nu, we're going to dx, I'm going to call it beta, and we get v beta. Okay. All right. It's looking okay. So now, if we impose that this thing is equal to this, right? Well, I'm going to do some relabeling. Okay. So this is something that I can always do with index notation. So if I'm summing over something, I might be summing over I. I'm always free to go, okay, I'm sick of bias. I'm going to call this J and change everything over here. As long as I'm summing over it, it's okay. I can do the same thing here. So I have alpha and beta, and I have mu and nu, and everything's being summed over. So let me swap. I'm going to say my mu's are now alphas, and my nu's are now betas. So what would that, let me just swap them. So I said, let's go alphas. So they swap. So this become mu, v mu. Let's change to alpha beta. This goes to gy beta, vx nu, v nu. Right? It's the same quantity. I've just relabeled stuff. But now it's still equal to this, and I see I have a nu and a mu. So these things don't matter. They're the same for all of them. But now that allows us to read off that g mu nu, dy alpha, dx mu, dy beta, dx nu g alpha beta, but that's a g prime. And then I'm going to inverse this expression because I always like to have my primes on the left equal to something times my other ones. So this is g prime alpha beta. When I invert these just go to the other side, right? So dx mu, dy alpha, dx nu, dy beta. Okay, so, and then it's just my g mu nu. Okay, so what was the purpose of this? This tells me that my object, the metric, must be a tensor, right? This is exactly what a tensor is. It's transforming by two lower indices. Remember, the lower ones have the x's on top, and it's given like this. So this tells me that keeping these things invariant under coordinate transformation is equivalent to using a tensor. That's pretty much what we expected, okay? But that's a good way to just see that for definite. Okay, I want to show the jiggery and pokery you can do with the metric. Okay, so leave those expressions. Let me just take this, okay? I have v mu, and I have g mu and nu. So I have two indices that are the same, so I'm summing over them. How does this thing transform? Okay, let's go through the rigmarole. dy d nu. So if this was primed, right? What would this transform to? So dy nu. So I'm going back to there. Sorry, that's a mu. We'll call this alpha, and then we get the alpha. The g transforms like this, big, long, messy. dx, and I just need to be careful with my notation. So I'm going to call this beta, and this is going to be the same, so that's going to be mu. And then I'm going to call this rho dx, rho dy nu, because it's the same as this index. And then we get our g beta rho. Okay. So, okay, whole lot of mess going on here, but I can see that dy nu and dy nu are the same. So I can do some index canceling, right? That's going to give me dx beta on top and the dx alpha on the bottom. Still have a b alpha, still have a dx rho, dy nu, and I still have a g beta and a rho. This quantity is this, we've seen this before. This is just our Kronecker delta, right? So this says that alpha and beta must be the same. So I can write them the same everywhere. That's very nice. Let me stick with alpha. So v alpha dx, let me write it suggestively, dx rho dy nu, and then I have v alpha and g beta, which now becomes alpha because they're the same, g rho. Okay, so what is this quantity? It's prime, so when it transforms, it goes to a dx and dy in the bottom. That's exactly the definition of a covector. So what we can see is that I can define v with a lower defined to be the metric mu nu times my original vector. Okay? So in this sense, G lowers indexes, which is very useful. This will be very useful. I'm going to toss these around like they're candy, okay? I'm going to, there's an equal sign there. If I can manipulate tensors because I can use the metric to raise up or lower indices. Okay, I just need to show one more thing. I showed it lower. Okay, because the metric is like this, I can relabel these either way, and we should get the same answer. So that shows that the metric is symmetric, right? I should be able to swap these two indices and should be the same. We already saw that it's like an identity matrix. That's symmetric. It's a symmetric matrix. You find that all metrics must be symmetric matrix. We also have that the only length that should be 0 is the zero matrix. Or is the zero vector. That's kind of a thing that makes sense. What that means is that our matrix is positive definite. I think, yeah, and not positive definite. It means our matrix is not degenerate. It doesn't have any eigenvalues that are zero. If you pair that with being symmetric, you have that the metric must have an inverse. Okay, that's very handy. I'm going to denote the inverse of the matrix with upper indices, right? Because you can check that it must transform with the opposite ways. Because if it transforms with the opposite ways, then the chain, multiplying them together with the chain rule will cancel out as needed. Okay, so if this is the inverse metric, we know that G inverse times G must give us the identity matrix, right? So what does that look like in index notation? Well, I'm multiplying a matrix, and as I said, that just means I have one index that's contracting as the sum over one index. So this must equal to the identity matrix, but the identity matrix is just our Kronecker delta. So we just take the uncontracted entities, which is mu and beta, and we write it like this, okay? So what I can do is take my quantity, this one here, right? So I have G mu nu, V nu, and I'm going, so I've said this is equal to, sorry, it's this one here. This is equal to V mu. And if I apply my inverse metric to both sides, so I'm going to apply it to this side, so let's say G alpha and a mu, so I need to sum over that. So this side, this is going to give me my Kronecker delta. So this gives me my mu and my beta, and on this side, I've applied my metric, G alpha mu, V mu, and then I have a leftover G nu. So, I'm going to get, sorry, mu and a nu, sorry. So this tells me mu must equal nu, so I can write that as V mu, and look, lo and behold, hold on, got lost in the index notation. That's an alpha. That's an alpha. And there's mu. Okay. So what this tells me is that the inverse metric applied to my lower index gives me an upper index. So this is what I mean when I say I can toss around my metric, and it will upper and lower indices on vectors. You can apply all of this to tensors as well. So this is a very important object because it's going to allow me to raise and lower indices and manipulate expressions like that.